Welcome to this webinar, Advancing Microanalysis Beyond the Limits of SEM EDS. My name is Stefan Böhm, Senior Product Manager for MicroXF and WDS on SEM based at Bruker, Berlin, and I will hold this webinar together with my colleague Michaela Brates, who is our Senior Application Scientist for WDS. Before we start, let me give you some housekeeping details. You should at this time be seeing the presenter slide on your screen. The presentation will last about 45 minutes. This webinar is also interactive. This means if you have any questions, you can ask them at any time during the presentation. To do so, press the Slido button when you access the webinar via the WebEx app. If you join us via browser, go to the Apps tab and then choose Slido. After the presentation, we will have a Q&A session to answer your questions. If we are not able to get to your question during this live event, we follow up with you by email. This webinar is also being recorded and it will be available as an on-demand version very soon. So now let's get started. Over the last couple of years, deconvolution routines for EDS have been significantly improved. So a relevant question for many users is whether they still need a WDS or the single EDS detector might be enough for their applications. This webinar will showcase application examples that goes beyond the limits of EDS, emphasizing the importance of having a WDS to complement EDS for challenging application. So WDS, or wavelength dispersive spectrometry, is well known for its superior spectral resolution and sensitivity. It is used on electron microprobes and also on SEMs to complement EDS for challenging applications. So it truly resolves peak overlaps instead of deconvolving them via software routines. And that makes the user more confident that an element is really present or not. So we can see here in that very typical example for a peak overlap molybdenum sulfur with an offset of 14 eV, that very fine WDS scan, which is where the WDS is able to very nicely separate molybdenum from the sulfur line, but that is not, but also you have the ability, or WDS has the capability not only to separate the main lines, you can also clearly see here the various X-ray family sublines, which are really nicely resolved, which you never will see with your EDS detector since they are lost in the background of the EDS. So WDS is very accurate, but it works sequentially, and therefore it's a relatively slow acquisition compared to EDS. So that means that EDS is more for everyday use, where EDS is used for specific application when highest sensitivity and resolution is needed. So a relevant question is, when we know that that WDS is very accurate, but it's also very slow, we need to understand a little bit the background or the working principle of a WD spectrometer. So WDS in general is based on Bragg diffraction using crystals. In a SEM, WD spectrometer are only available as a parallel beam optic. With a parallel beam optic. That means there is an X-ray mirror optic, which you can see over here, which is placed near or very close to the sample and transform the X-rays diverging from the sample into a parallel beam. The characteristic X-rays will be diffracted by a flat analyzer crystal, which is located here on the crystal turret and counted by a proportional counter used as an X-ray detector. In order to count X-rays of a specific wavelength, the angle theta needs to, which you can see over here, needs to be adjusted by rotating the crystal torrent relatively to the sample. And that angle theta determines the angle that is required to detect X-rays of a character for a specific wavelength. But also the detector rotates to set the right diffraction angle to satisfy the Bragg's law, which you can see over here. So in that way, a range of X-ray energies can be analyzed sequentially by using EDS. And diffracting single X-rays on a diffractor or on a crystal provides a much higher peak-to-background ratio and hence much better detection limits down to the lower ppm range. And that is a huge difference to EDS, where EDS, it's much more effective by the Bremsstrahlungsbackground, which limits limits your detection limit. A very typical use case to use a WDS is a range scan. Range scan means that the user defines a specific elemental range or energy range for scanning. So here in that case, I want to dwell on the molybdenum sulfur example from the beginning. So we have here our EDS peak containing molybdenum sulfur, not deconvoluted, and we want to check with the WDS if there's something more visible. So what we are doing is we're setting here the start energy around 2 keV, and then we run our WDS scan. You see here how the intensity profile for each individual energy, which will be collected sequentially, and you see here how very nicely the various peak sublines will be deconvoluted. So the user can be really sure that there's both in there, that we have molybdenum, and you can see how the different sublines, but also the sulfur peak. And here you can see what's happened inside the instrument during data acquisition. So we have here, see here our mirror optic, which stays fixed in space, so it doesn't change with the X-ray energy. The only thing what changed is here the crystal, which is mounted on the crystal turret. That changes. There is the theta angle will be changed, and also what we have learned in order to satisfy Bragg's law, also the angle of the detector relatively to the crystal needs to be adjusted. So WDS is an addition to the EDS workflow. It comes on top of your EDS that provides and can provide the user the next level of certainty. In the common law, in the common language, WDS is referring to traditional EDS or classical EDS, which is used on electron microprobes. So this instrumentation provides a very high spectral resolution and a very high peak-to-background ratio. It can cover a broad range of X-ray energies, but the drawback is that of that instrumentation is that the solid angle changed with the X-ray energy. So it gives you a very high sensitivity for higher Z elements, because there's an optimized geometry for that energy range, and therefore you achieved the best detection limits for these energy regions. So it works strong for very high or for higher energy X-rays, but it's weak for lower energy X-rays. This is because not only that we have a divergent X-ray beam. Divergent means the X-ray beam is not concentrated, so it is divergent, which means that only a very small portion of the X-rays will hit the diffractor for low energy X-rays. And that is because the sample to the diffractor distance, and therefore also the diffractor to detector distance, is very large. So that means you can compensate that loss in intensity by increasing the acceleration voltage and the beam current, but that makes it not accessible for nanocharacterization or microanalysis tasks. So it gives you a very low CPS rate at low SEM kV, and therefore it's only very limited applicable for nanocharacterization tasks. Commercially available WD spectrometer for SEMs are, what I mentioned at the beginning, are based on a parallel beam optic. Here we have a large solid angle, which is nearly constant for all X-ray energies, because what we saw in the animation video, the distance from the mirror optic to the sample doesn't change. We have a concentrated focused X-ray beam and a high sensitivity for low energy X-rays or light elements. This instrumentation can run in the 5 to 10 nanometer range, and Bruker WD spectrometer covers an energy range starting from 70 eV up to 3.6 keV. There's also another PBO BD spectrometer brand, which covers a larger elemental range, which goes to 10 or 12 keV, but this is a little bit at the cost of spectral resolution. So our spectrometer is really designed for the lower energy range, since especially in that energy range, we have the majority of peak overlaps occurs in that energy region. So that instrumentation is ideal for light elements application. It can run at low SEM KV, and therefore it's highly applicable for nanocharacterization application. To give an example on that, that is a boron and steel sample, which you can see over here. That's a simultaneous EDS WDS acquired method, was acquired at 5 keV, 17 nanometers. And when you look here at the scale bar, the small boron inclusion, which are in the nanometer range at 0.48%, we can clearly see that very strong boron signal acquired with the WDS. And those four structures of light elements here in that particular case for boron are definitely not possible to analyze with traditional WDS, since what we have learned, there are higher SEM KV settings required, but it's easily accessible or easily possible with a PBO-based WDS. Talking about EDS, if EDS can detect those small inclusion of boron, here you can see a short comparison of the peak intensity for boron acquired exactly at those conditions. And we can see here that compared with the standard EDS, that very strong peak of WDS compared to the relatively low peak with a standard EDS. And even when we compare the peak intensity with a windowless detector, we can see here the intensity for the windowless detector is increased, but it will never achieve that high peak intensity which you can gain with a WD spectrometer based on a parallel beam optic. That means when we're talking about limits of detection with EDS in general, we can achieve for boron 5,000 ppm. With EDS, we have an improved detection limit by a factor of 45. So conventional EDS cannot detect boron at these lowest concentration levels. That might be possible with a windowless EDS, but still the boron signal will be very noisy at these lowest concentration. So, and even when you have greater counts for the EDS, that also means that the background will be higher, which will not improve the peak to background ratio for EDS significantly. So when it comes to trace element detection for low energy X-rays at the nanometer resolution, a PBO-based WDS spectrometer is way more sensitive than any EDS, even if it's standard or windowless detector. So in that particular case, we talk about boron, but let's take a look at the entire energy range which can be covered with the Bruker WD detector. You can see here on the x-axis the energy which can be covered with instrumentation up to around 4 kV. When we look on the y-axis, we have here our full width and half maximum, and we do not need to talk about all different elements, but you can easily see that the spectral resolution of WDS is generally better than EDS by a factor of 20. But what you also see that here, that the WDS comes with various different crystals or multilayers. So here we have a PET multilayer, we have a TAP multilayer, 60 angstrom multilayer, 80 angstrom multilayer, and 200 angstrom multilayer. There is obviously an overlap between that various crystals. So for example, when we focus here on oxygen, we can see oxygen, or we can detect oxygen with the TAP crystal, with the 60 angstrom crystal, as well as with the 80 angstrom multilayer crystal. But what we also see is when you when you go for oxygen, for spectral resolution, and when you choose TAP crystals, that gives you a much better spectral resolution compared to the 60 angstrom multilayer. The picture will change a bit when we look for the detection limits and we dwell on our oxygen. Here you can see that with the 60 angstrom multilayer, we are way more sensitive than using the TAP crystals. So that is considered in the software, and the user has the ability to choose either for best spectral resolution or for maximum throughput. And depending on the user settings, the right crystal or the correct crystal will be selected, automatically selected. So for the limits of detection, you can see here that WDS gives a 10 times higher signal-to-noise ratio, which will result in 10 times lower detection limits, which makes it highly applicable to detect low levels of traces with the WDS. Those values here, this is always collected for standard EDS detectors. They are not set in stone. You see here the KV settings for the data acquisition for EDS and WDS. So that varies a little bit, but it will never change. It will not change the big picture. So I think everybody knows the limitation of EDS. So in terms of spectral resolution, and that is for sure considered in the deconvolution routines, which have been, I already mentioned at the beginning, has been significantly improved over the last years. So it works great for most applications. You can see here the silicon tungsten peak and the deconvolution for that silicon tungsten that fits really nicely. So that has with EDS, it has a 35 eV offset. But also deconvolution, that is the same as every scientific hardware instrumentation. It has its limitations, but here it's a software algorithm which also has its limitations. So when we look at the limitation for that deconvolution routine, the question is how that behaves for overlapping peaks when they have a very small offset. So a very small offset means smaller than ATV. So remember, even when you have a very good EDS detector, your EDS resolution for specific elements will not be better than 40 eV. How it behaves for overlapping peaks when you have a large difference in concentrations, for example, you have 89% of silica and only 2% of tungsten, or how it behaves for low concentrations in general if you have low count statistic for EDS due to the higher background. Here in that particular case is relatively simple because silicon and tungsten are distributed in high concentrations. So the solution that if you really want to make sure, if you want to really prove which elements are in, then is WDS the ultimate choice, because as we already saw, WDS can truly resolve the peaks and makes the user way more confident if the element is really present or not. Here EDS is always based on deconvolution, and with WDS you can really see if the elements or if the peaks specific elements are really in the sample or not. So for application involving very small peaks overlaps and low concentrations, it's fundamentally better to resolve peaks than to deconvolve in order to provide more reliable proof of the presence or absence of an element. And this you can only do with a WDS. So before I will pass the microphone to my colleague Michael, let me summarize the important points which we have identified so far. So WDS is high sensitivity for the detection of trace elements down to lower ppm levels. You can see on the right hand side that lower part spectrum of a stainless steel with trace of manganese, where you can see that WDS is capable to detect that very small amount of manganese, even here in that low energy rate region. So For sure, there can be a relevant question why we are not going to higher to the K lines of manganese, because they are obviously more intense than the lower energy lines. Yeah, maybe an answer can be that the user is interested to maintain the spatial resolution to work at low KV. And even at very low KV, you can see here very nicely that small amount of traces. We have saw that resolving is fundamentally much more reliable than deconvolving. You can really see in the spectrum if an element is present or not. You can even see the various X-ray family sublines. So the best spectral resolution, if you have a really good EDS detector, is not more than 40 eV. So for overlapping with a very small offset, you need to trust what the deconvolution engine will suggest you or tells you. WDS can reach up at 20 times higher spectral resolution and up to 50 times better detection than EDS. A PBO-based WD spectrometer is very strong for light elements or low-energy X-ray application. It is highly applicable for nano-characterization at low KV settings. This is where traditional WDS struggles, and even EDS when it comes to low concentration levels. So now I want to pass the microphone to my colleague, Michael. Just a quick reminder, if you do have already questions, you can type in your questions and let us know. So with that, I will hand over the microphone to Michael.
Thank you, Stefan, for this very nice introduction. And hello, everyone. I'm happy to have you all here. I'm Michael, and I will show you now some applications that really make a difference. So applications where EDS faces its limits and WDS can surpass these limits. So the first example is on a complex metallic sample where we investigated the contact zone here between the metal substrate on the lower left, lower right, and the major coating layer on the upper left. Here we see the EDS spectrum on the right, derived from a spot analysis, and showing 8 elements that were identified automatically. And we go into detail looking at the deconvolution result, where the background is subtracted and overlaps are sorted out by modeling to check if every element was correctly identified. With the Bruker software S3, we clearly have the best deconvolution software ever. It is very intuitive, so we can go into details here. We zoom in on the overlap of the silicon K peaks with the rhenium M peaks. The measured spectrum is displayed with the dark red outline here, and the two peaks are shown fitted. The two fitted peaks are shown with red and yellow color respectively. And what we see here, obviously some elements are missing from identification. When we check for all potential overlaps, we find as much as 11 additional elements that have X-ray lines in the region of interest. Really a zoo of elements, and it is highly unlikely that all these elements are present in the sample. We can reduce it to a minimum of 4 additional elements in the sample. Additional to silicon and rhenium, there seem to be tantalum, tungsten, osmium, and zircon. All of these are present in this sample with more than 1 weight percent, according to this deconvolution fitting and the resulting quantification results. We may leave it like this, or maybe not. So can we fully rely on the EDS results here? Can we? or should we prove it? Should we get more evidence? And for this, we take the WDS and make a range scan. This is what we see on the right-hand side. We scan across the energy region of interest, and we clearly see the major elements, silicon and rhenium. But we also see small peaks for the tantalum here, M alpha and beta. We see peaks for iridium, M alpha and beta, and we see gold. So we clearly identified the present elements by help of WDS. Yeah, the EDS deconvolution often works well, but it runs into difficulties when we have very strong overlaps and the intensities of the peaks are very different. So like Stefan already pointed out, or what we see here, a very intense peak for rhenium and for silicon and very small other peaks. So that is hidden for the eye of the EDS. Okay, you might say this is a very complex sample with too many elements at once. But so we have now a look on a very simple sample here. This is a semiconductor microsensor. It consists of tantalum and tungsten. So here's the tantalum, here's the tungsten. And we made some analysis on the tungsten here to check for the elements. The spectrum shows tantalum with the M lines here and even the N lines. And we also see oxygen and carbon, which is derived from surface adsorption. So we didn't plasma clean the sample before analysis. When we zoom into the spectrum here, we see the broad peak here for tantalum. We cannot distinguish between the tantalum M alpha and M beta. When we run a WDS range scan across the area, the region of interest, we clearly resolve the peaks for tantalum M alpha here and tantalum M beta. And in between, we find silicon. This is the silicon K line. And yeah, it's the same analysis, the same spot and the same sample fit. Here we see both together, the EDS deconvolved spectrum, no indication for the silicon. This is WDS, a clear indication for silicon. A small peak, a small amount of X-rays that is hidden for the EDS. And what we discuss here with a small peak, it displays 5 weight% of silicon in the sample. 95% is tantalum and 5% is silicon. So it's not a trace actually. And limit of detection of 5 weight% silicon, that is not very good. But we have to say this is a really unfavorable situation for the EDS when we encounter tantalum and silicon at the same time. The fun part about this sample comes here now. The signal for the silicon is actually not from within the tantalum, but from below. It's the substrate, actually. Using higher kV, such as 5 kV here in the lower row, we clearly see that the excitation volume penetrates the tungsten and the tantalum and goes into the substrate. So here's the tantalum layer and there's the silicon substrate. So we clearly pass through the upper layer. And this is easily shown by the EDS spectrum, clearly by the WDS as well. We can see it in the map and everywhere. At 3 kV, on the other hand, it seems from the EDS data that we are still within the tantalum layer with the excitation volume, no indication for the silicon. With the WDS, we clearly see the silicon signal. So at the end, the layer is thinner than previously thought. Let's have a look on geological samples. I'm a geologist, by the way, and I like minerals. Plagioclases, like we see here on the right side, are common minerals, common in the Earth's crust, and in volcanic rocks, they can record the magma evolution. So with their crystal zoning and changing in composition. There are these plagioclases are solid solutions between a more calcium-rich and more sodium-rich end member. The calcium-rich variants, they can incorporate traces of the element strontium and incorporate it in their crystal lattice. Unfortunately, the strontium L line is strongly overlapping with the silicon. So it's very close and it's a trace element. Then you see the strontium here in the EDS spectrum. You can't. I think no one can. No deconvolution algorithm can do that, and no windowless detector can see the strontium as a trace element that is heavily overlapping with the strontium, with the silicon, the major element peak. Here in the WDS range scan, we clearly see the peak for the major element, the silicon K alpha line. This is silicon K alpha 3,4, the satellite. And here is the strontium peak. Can you see the strontium peak? I guess you can't, but it doesn't matter. This small peak is 170 times smaller than the silicon peak. So we have to zoom in. So this is the difference in ratio, and we zoom in, and here we clearly see the peak for strontium L alpha, a trace element, and here's the major peak of silicon K alpha. And we can even map the distribution of this trace element, strontium. To the right, you see the map, and you see that the trace element is concentrated in two areas within the zoned crystal here, and there's less strontium in the rim of the crystal. And this is valuable information for the geologists. Let's go on with more trace elements, in this case on steel. This is a certified steel sample, and where we know the accepted or expected concentration of the traces. This is a martensitic stainless steel with major elements chromium and iron clearly, and a lot other traces. And we picked some of the traces and compared the EDS and WDS results. Some traces we were interested in is molybdenum and sulfur. There's sulfur added to this steel in trace amounts, and this is the EDS spectrum. Here is a peak. You should believe me. This is the peak for strontium, for sulfur in yellow, and a peak for molybdenum in violet. So two very small peaks, strongly overlapping. And the background is immense. So we have a very bad peak to background ratio. And clearly, it's really hard to quantify this trace amount of molybdenum and strontium and sulfur, by using EDS. When we make a range scan by WDS, we clearly see the peak for molybdenum, the L alpha peak, and the peak for sulfur, the K alpha peak here. And with this information, it's much easier to quantify the amount of the trace elements, sulfur and molybdenum in steel. And here to the right, we see the table with the results given by EDS and WDS for sulfur and for molybdenum. And we also see some other traces that we determined by both methods, EDS and WDS. And I picked this here as an example, silicon in steel, just to show you it's not all about overlaps, but it's also about the peak to background ratios. So here we see the EDS spectrum. This is the silicon peak, and here is the nicely resolving WDS derived peak. For EDS, we have a peak to background ratio like this. So the ratio is below 1. The peak is smaller than the background. And for WDS, we have a much higher peak and a small background, so a much more favorable ratio of peak to background. And this helps a lot to get to low detection limits. Now we have a look on semiconductor samples again. And this example is on nanowires. Nanowires are high-tech semiconductor materials. They are very small, clearly, by definition. In this case, about 200 nanometers in diameter. So it means it's very challenging to analyze these samples, but our customer, Eric Robin from CEA in France, he managed to do so. He managed to discretely analyze single nanowires for his study. So he had to reduce the primary energy to 4 kV and a low beam current of 5 nanoamps to stay within a single nanowire. And he checked with different acceleration voltage. When it's too high, he gets too deep down. So he had to reduce it to 4 kilovolts. And the task is clearly here we need high spatial resolution for the analysis, as well as high spectral resolution or energy resolution, and high sensitivity for low contents, because the task was to measure the content of the dopant magnesium in the top layer in the gallium nitride part of the nanowire. Using EDS alone, he could not solve this problem because the magnesium is hidden in the tail of the gallium peak. Here's the gallium peak or the gallium L peaks. Here's the nitrogen peak that we expected. Here's also carbon from the surface. Yeah, the magnesium is completely hidden. Doing some modeling, we can see only with concentrations of for the magnesium above 1 weight%, we would be able to see a small peak by EDS. But the concentrations here are much lower than 1%. So the only solution was to use the WDS. Here's a range scan across the nitrogen. This was to confirm that there is no indium overlapping, so to confirm that analysis is really confined to the upper part. Here's a scan across the gallium L lines and showing also the magnesium K alpha peak. So we clearly see a peak here, and this can be quantified. We can do a peak background measurement and compare it with standards. And he received a concentration of 800 ppm for the dopant in the upper gallium nitride layer. So determination of trace elements in semiconductor nanowires. And it's hidden for the EDS. Now let's have a look on light elements, and because this is also a really good application for the WDS. The present WDS with a parallel beam optic is very sensitive for the light elements, such as boron. And here is a mapping of a steel sample, customer steel sample. The lower half is the steel, and the upper half, this is a dispersion layer on the steel. Nickel, phosphorus, boron dispersion layer. And there is crystallization of different phases of borides that we see here. The image that we get by WDS is much more detailed, much less noise, much better image after 5 minutes. So this was simultaneous acquisition by EDS, a conventional EDS, and by WDS, and we see how sensitive the WDS is, so we get much better statistics with the WDS for this element. And yeah, we can combine the information of EDS and WDS. Here's EDS data on the major metals, iron, nickel, and boron data from WDS. Yeah, one example with a conventional EDS, this is certainly a bit unfair for the comparison. For the light elements, we would clearly choose a windowless EDS because there is no absorption in the window. So a windowless detector would do the mapping faster and also give a nice image after 5 minutes. But the problem where the windowless detector gets stuck are the low contents. And here we have an example of low boron amounts on a silicon germanium semiconductor material. To the right is the EDS spectrum of this material recorded by the windowless detector. We zoom in on the lower part of the spectrum and see the deconvolution, and we are missing the boron signal. We cannot see the boron in this sample because we are obviously below detection limits. So these there's 2 samples here. They contain 1,500 ppm and 600 ppm, which is too low for the windowless, very sensitive EDS detector. But yeah, even that one has limitations, and we can surpass it with a WDS. So here is the WDS range scan across the area or region of interest. And we see here, this is the trace of the background. And this here is the peak for boron in the sample with a slightly higher content. This is 1,500 ppm of boron, and we can clearly use this and quantify the boron content in the sample, whereas the EDS couldn't. Now let's get back to minerals, since I like minerals. And this is an example for beryllium-containing minerals, 2 different types, so beryl and tuctopite. They contain several percentages of beryllium. Beryllium is, the beryllium K alpha line is at 109 electron volts. So very much on the lower limit of the energy range of the X-ray detectors, EDS and WDS, also difficult to get by a conventional EDS. This is what we see here. This is the deconvolved spectrum acquired by a conventional EDS, and we see no indication for the beryllium. So too much at the end, and there is absorption in the window of this detector, and there's so much overlap with the silicon L line and the aluminum L line, so it cannot be seen. The windowless detector with a large surface is much more sensitive, so we get much more counts here in the low energy region. However, this can be well fitted with silicon and aluminum alone. So only when we expect beryllium and choose this as an add-on, it will be fitted somehow in the spectrum. So we can fit some beryllium here with a green color. And yeah, well, we get to some quantification results. However, the error is quite large. When using WDS, this is a range scan for WDS for 4 different minerals. We can clearly separate the beryllium K alpha peak from the silicon L peaks in the beryllium containing minerals beryl and tuctopite, here marked with a beryllium peak, shown in comparison with the beryllium-free minerals albite, no beryllium peak, and olivine, no beryllium peak either. All of these 4 minerals are silicates, so they all show the silicon L peak. And finally, let's have a look on nitrogen as a further light element, and here's nitrogen contents in steel, low nitrogen contents between 100 ppm and 1800 ppm in certified steels, with a conventional EDS having a super light element window. Most of the samples do not show the nitrogen. We are below detection limits. Only those samples with somewhat elevated contents show some values, but there's a lot scattering. Doing the same measurement with the windowless detector, we see a signal for the nitrogen, but quantification is really difficult. There is a lot statistical error. So because we are close to detection limits, and it's quite difficult. And we're using the WDS with a clear, good peak to background ratio, we can get to much better values. Values here shown with the green dots that show good correlation between the measured values and the certified values. And with this, I would like to end and give a summary here. So use the WDS or whenever it comes to resolution of peak overlaps, so you don't miss any element from identification and achieve more accurate results. Use the WDS for trace elements to push the limits to lower contents and quantify these low contents, and use the WDS whenever you want to measure light elements, because it's much more performant than any other EDS and any EDS, windowless or windowless clearly also. And finally, the system with the optic here, our present WDS, can operate for high spatial resolution using low KV. And thank you very much for your interest, and we're waiting for your questions.
Yeah, thanks, Micha, for your excellent presentation. We will now have our question and answer session. Will be last about 10 to 15 minutes. So if you do have any questions, feel to submit them to us. We already have a number of questions coming in. So there is a question for you, Michael. How long does it take to do a mapping for the sample at page 35 with WDS? Maybe we need to go back to page 35. Sorry, I should have gone there. 35. So this.
I was still muted. Sorry, this map was acquired in 5 minutes, like it's said on the header. So it was, just a check stopped here after 5 minutes, and it was sufficient because the WDS has a very high sensitivity for boron, for the lowest energies, and for the EDS recording the major elements, it was also sufficient time, 5 minutes. It depends, mapping in general, it depends on the signal. So if the signal is intense enough, it can be short. But some other samples, like we could go for with the trace elements, distribution of a trace element, signal from a trace element is clearly very small. Yeah, you see the count rates here, so that takes a long time. That is an overnight mapping for trace elements.
Yeah, thanks, Micha. So there's a question perfectly for me. How does WDS EDS compare to microXRF EDS? Yeah, that's a really relevant question, to keep it short and simple. So we're looking for trace. Maybe some of you know that both techniques are highly sensitive for traces. As we pointed out, WDS, let me say it another way, if you are interested in spectral resolution and we can go with WDS for the lower energy range. So you can see here in our examples how WDS is able to pick up the very low amount of traces to up to 100 ppm for the M and for the L lines. Compared to that, MicroXF, or let me say in general, everybody knows that the higher K lines are more intense than the lower energy lines. So MicroXF is a perfect technology to pick up the higher K lines, so which leads to a limit of detection down to even 10 ppm. But that is a little bit of the cost of spectral resolution, since MicroXF, as the name already indicates, it works on a micrometer base. So there are used polycapillary X-ray optics, which have a spot size of around 30 micrometers. There is another question. Is it possible to change diffractors to change the sensitivity for low or high elemental range? If so, in brackets, if customer works with low energy range, can we modify the diffractors? So let me answer that. So maybe you remember the slide I shown where we compare the spectral resolution and the limit of detection. So that WDS Bruker WD spectrometer is specifically designed for the lower energy range, which can cover a range up to 3.6 or 4 keV. So since it works with an X-ray mirror optic, we cannot go beyond that energy range, even when we change the diffractors. Yeah. So the reason for that was that since the majority of the peak overlaps especially occurs in that energy region, we want to be really sensitive in that energy region to have the best spectral resolution which a WDS spectrometer for that energy region can provide. There is another question. Maybe that is for you, Michael. So that's the question: is WDS quantification complicated?
For me, I think it's not complicated. So, well, with EDS, you have standardless quantification, and the most simple way it could be pressing the button and letting the automation do its work. I always recommend to use our perfect deconvolution interactively, so check for the quantification results, that every element is identified by EDS. So, but yeah, WDS needs standards, so that may be a sort of complication. So you need to measure standards along or with your samples, or at a time you need some standards because you need to compare the count rates of standards with your sample. There is no way to use a standardless quantification. But this is fully implemented in the software, and at the end, not a great deal. So it's not complicated, I would say.
Okay, Micha, there is another question. I think that's also for you. How we determine the minimum detection limit in EDS, WDS, and what parameters controls it. That was on page 8. Maybe let me go back. That was that one. This one.
Yeah. On the right-hand side, we see the detection limit. That is this detection limit that is shown here, that is only valid for the given conditions, 10 kV, 5 nanoamperes. So it can be improved with increasing the beam current. So a higher beam current means more signal, and the higher the signal, the lower the statistical error. That would improve the detection limit. And the other factor is with the excitation volume, or the primary energy. So for the higher X-ray energies, so say everything above 1 kV, you could increase the detection limit by increasing the acceleration voltage. You get a larger volume, which means more X-rays, and this again, more counts, this will increase the detection limit. On the other hand, let me add that for the low energy side, so for the light elements, it's important to decrease the acceleration voltage because absorption in the material is very important. So with 5 kV, you could get to better detection limits for the light elements that we see here, like boron, carbon, nitrogen, oxygen, and so on.
Thank you, Michael. There's another question. So, does WDS equipment cost more or less than WDS? Yeah, let me answer this question more generally. So, WDS is more expensive than EDS, and that is because it contains a huge amount of mechanical parts. So, which are definitely more expensive and a little bit more complicated than an EDS detector. And there is another question. This is a little bit related to the comparison to SEM Micro XRF. When to use SEM Micro XRF? When to use when to use WDS? Is it separated by particle size, type, or samples? So or sample type. So maybe you remember, so there already was a question related to XRF. There's one difference. Not only the spectral resolution or the spatial resolution. There's also a difference in the sample types. So micro XRF will not charge. So it's an XRF excitation. It's not a detector, so that will not charge samples. So with WDS, we dwell on the electron beam, and the samples needs to be electrically conductive. That's a little bit more, or let me say, it's easier when you go to low KVs, and the requirements for the coating are not that hard as when you go to higher SEV and KV. There's also one other question that I can also try to answer, but we are planning to purchase a sample heating stage. Are those stages compatible with WDS or not? Hard to answer. So we do not make any experience with heating stages in combination with WDS. So it's really hard to make a statement on that. If the temperature has any influence on the WDS optic or not. What we can tell is that the distance from the sample to the optic is always 18 millimeters. So there's huge amount of space between the samples, so there should be enough gap so that the WDS will not heat up. But it cannot promise. What we definitely can promise that the optic is fully retractable. So if the stage is only used in, let me say, in conjunction with EDS, then it should be definitely no issue. And there is a final question before we running out of time. Is for the LOD, you pointed out it depends on the KV and other factors. Can you elaborate this? Michael, do you want to take this?
I think this is quite similar to the other questions we had before, and it refers to the, so it's what we see here. We give the LOD, the limit of detection, for 10 kV and 5 nanoamperes. So increasing the kV, we get better results for the higher energies, but worse results for the low energies. So we lower the kV to get less absorption and get better results for the low kV, for the light elements and so on. And higher beam current in general gives more counts, and that improves the statistic. Thank you. Bye.